All right, so in this video, we are going to be taking a look at exponents. Again, you guys have probably already seen these a little bit. This is more going to be a refresher of how exponents work and a little bit of how they work with the metric system. So real quick, fast refresher, exponent just means how many times you multiply this number. So to give a quick example, so 2 to the third, that means you do 3 2s and you multiply them all together. Pretty straightforward stuff. Meanwhile, multiplying and dividing exponents gets a little bit trickier. But the long and short of it is that when you multiply exponents with the same base, or I'm sorry, when you multiply values with exponents, if the base is the same, you add the exponents. And real quick, let's switch over and I will demonstrate why. So let's say we've already established 2 to the third is the same as 2 times 2 times 2, right? So let's say we multiply that by 2 squared. So that would be 2 times 2. And I think you can see where we're going with this. If we're just multiplying all these 2's, well, we know we have 3 2's multiplied here and 2 2's multiplied there. So that would mean the total number of 2's we have is 5. You can even do this if you don't know what the power is. So let's say we have 2 to the x multiplied by 2 to the fourth multiplied. So that would mean that we get, actually it's probably better with just the dot. Multiply, so if we multiply these, so we have x number of 2's and we have 4 2's, so the new power should be those two numbers added together, so the new power becomes x plus 4. So even though we don't know what x is, the second someone gives us a number, we'll be able to figure it out. So let's say there were 7 of them. Well, if this was a 7, then this would be a 7, and we know that the final version would be 2 to the 7 plus 4. 7 plus 4 is 11. We'd be able to fill that in. So, able to do that quite nicely. So now let's talk about the division side of things, just for a second. And say we had 2 to the fourth over 2 squared. So we could multiply that out and do our like fractions and stuff, but that's going to take way too long. So let's just say, so we know we have 4 2's on top and we have 2 2's on bottom. So according to our rules, since they're all being multiplied, we can cancel those 2 on the bottom and we're just left with 2 times 2, which would be 2 to the second. Faster way to do it, much faster way to do it, is on top we have 4, on bottom we have 2. So, according to our rules, 4 minus 2, because that's how many are being canceled, that leaves us with 2. So this is the new power, which means that we can skip all of that stuff there that we did on the bottom, all of that showing how it all works. We can skip all of it and just say, oh, I know how this works. I know that they're going to cancel like that. I can just put 2 to the second because 4 minus 2 is 2. And because I know negative numbers scare some people, we're going to do some with negative numbers. So let's say I have 5 to the 10th over 5 to the 15th. So the rule still applies. We're still doing the top one minus the bottom one. It's just that now we're going to get a negative answer. And that's okay. You can get negative powers. Negative powers do serve a purpose. They are important. We're not going to go too heavy on them right now. Just know that that's a thing. So 10 minus 5, that would be negative 5. So we have 5 to the power of negative 5. That would be our answer. And that's how you multiply and divide exponents. Now, one thing I want to point out is that unlike fractions, we don't really add exponents. We don't really add or subtract exponents. Multiplying and dividing is really all that we do with them. And even then, it's only if they have the same base. So like if we have 2 to the something times 2 to the something, you can add those. But if, say for instance, let's go back to the board for a second. If you have, there we go. So if you have 2 to the something times 2 to the something, you can add those guys. But if you had 2 to the something times 3 to the something, we don't do anything there. This is how we leave that because the bases are different. And base just means the number that has an exponent. So since the bases are 2 and 3, those are different. Oh, I can't do anything to it. I would just have to leave it alone for the time being. So, real quick, back to the presentation. So back to what we were talking about. So now let's talk a little bit about magnitude and scale. So this is a big chart, a lot of stuff on it. We're going to talk about it for just a couple of seconds. So in the metric system, we have units, and then we try to move up by powers of 10, or we try to move down by powers of 10. So for instance, let's say we're talking about weight. So in the case of weight, units would be 1 gram. So 1 gram is, so much of the centimilli micro nano. So basically, the bottom is the smallest, the top is the biggest. So we're talking about grams. A kilogram is equal to 1,000 grams. And you can get there by multiplying by 10 to the third. So real quick, let's jump over to the blackboard for a second. So let's say I have 3 kilograms, and I want to know how many grams is that. Well, I know that 1 kilogram is 1,000 grams. So, 3 times 1,000. That is going to give me 3,000 grams. And that's about all I need to know when I'm moving up the chart. So going back to the chart, so if I wanted to move up from a certain, or I'm sorry, if I want to move down the chart, if I move down the chart, I multiply. So if I want to go from kilograms to just grams, I just multiply by 1,000 because that's how many I need, and so on and so forth. So however many down you're going, you're multiplying by that big of a jump. And the same's true in reverse. So if I had, say, 3,000 kilograms, or I'm sorry, not 3,000 kilograms, that's way too much. If I had 3,000 grams, I could divide by 1,000 to turn them into kilograms. But we use powers of 10 to kind of give us a good sense of scale here. Because, there's a huge difference between 1 gram and 1,000 of them. There's also a difference between 1 in a million and 1 in a billion. And so being able to clarify exactly how much that is really, really useful. So, for instance, if I have a kilogram and I want to express that in grams, when it's like, oh, okay, so a kilo is 1,000 grams. So however big a gram is, is that many. So if we're talking lengths in meters, so let's say we have 1 meter. So 1 meter is about as wide as a door is. And so you go, okay, I know how wide a door is, for the most part. I've walked through a door before, or I've seen them. Maybe you've seen them on TV. So, we know how big a meter is. But a kilometer is 1,000 meters. Now, I don't know about you, but a lot of people, and I mean a lot of people, have a really hard time picturing 1,000 of a thing. So like 1,000 doors lined up left to right. That's a lot of doors. I don't know if I can honestly picture exactly how wide that would be in my head, which is why the metric system exists. So I don't have to remember a kilogram as 1,000 doors. I can remember it as something a little closer. So like a mountain is usually about 1 kilometer tall. So like the average mountain is about 1 kilometer. So it's like, okay. So I have a vague understanding of how big that is. So kilometer or a kilometer is really big. Okay, that makes sense to me. And then we move up to something bigger, and it's like, okay, so let's go to mega. A megameter. Okay, so how big is a megameter? It's 1,000,000 meters. And I'm like, wow, that is a lot of doors. But I don't have a frame of reference for that. I don't know how big 1,000,000 doors is if I stack them, all I don't know how wide that is. So instead, it's like, okay, so a million. Okay, so millions. So kilometer is to a megameter what a meter is to a kilometer. So if I'm going up from a meter to a kilometer, that's about 1,000 times. Okay, so that's from like a door to a mountain. Okay, so a megameter is like really, really big. Like it's probably like at least we're talking like planet size now. Because, a door is not that big relative to a planet. A mountain, it's a bit bigger, but it's not quite there yet. Meanwhile, oh my goodness, if I did that same kind of jump off of a kilometer, yeah, I'm going to get about half the width of Pluto, which is, in fact, a planet. It's the smallest planet, but it is still, well, NASA decided it's not a planet, but it's on a planet scale, if that makes sense. And then there's the gigameter, and you're like, oh my goodness, a gigameter. So we jump from a mountain to planet size, not exactly a full planet. It's like Pluto size, so it's like kind of a planet. But now we're making a jump from there to bigger. It's like, oh my gosh, that's got to be massive. That's got to be huge. And yes, it is. A gigameter is about the width of the sun. So it gives us a better idea of how big that jump is, the magnitude of the jump, you might say. And so if moving up means we get that much bigger, moving down means we get that much smaller. So a meter to a kilometer is like a mountain to a door. Okay, so then if the kilometer is the mountain, the meter is the door, that means when I jump down again to a millimeter, because millimeter is the power of 3. Centimeter is just on here because everybody, you look at a ruler, you see centimeters on there, so you can get a decent understanding how big it is. It's about the size of a staple. So then we're going to a millimeter. It's like, okay, so if a mountain is to a door, then door is to about a piece of paper. So this is pretty tiny, which makes sense. I'm pretty sure if you laid a door at the base of a mountain, it wouldn't seem that big. So meter to millimeter. Okay, so this is a piece of paper. It's really small. Okay, fair enough. The height of a piece of paper. So not the length, the height of a piece of paper. It's pretty small. Fair enough. Well, what if we made a jump that again down to something smaller? It's like, oh my goodness, well then it's got to be like really tiny. We got to be talking like cells and stuff. And yeah, we're talking about the size of the height of a blood cell, not the width of a blood cell, the height of a blood cell. And oh my goodness, that is very, very tiny. And then we're going to make it even tinier. Oh my goodness, now we're getting down into molecules. And so that's the idea, is that when I say what kind of measurement it is, you'll understand what kind of scale we're looking at. So, if someone's 3 meters away, they're not that far away. If someone's 3 kilometers away, yeah, it might be a while before they get here. If someone is 3 millimeters away, then oh my goodness, those people are very, very close. Maybe they should back off some. Maybe they should move away. Just a little bit. Need my personal space. So, but anyway, that's why the oh, I switched slides. Didn't mean to do that. That's why the metric system works the way it does, and that's why a lot of people use the metric system, because, once you kind of get used to how big these are generally, gives you a good sense of scale for what kind of a measurement you're taking. So now, scientific notation is a lot to do with exponents. So like up here, when we're talking powers of 10, it can make those a lot easier, which is why we're going to go over it. So real quick, let's switch over back to the board real fast. I'm getting notifications. I'm going to ignore those right now. Okay, so we are working on this stuff. Okay, so let's say I have 125 kilometers, right? And I want to write that in scientific notation. So here's the thing. Scientific notation is all about scale. So like with the metric system, it's all about how many powers of 10 are we working with here. So 125 kilometers is gonna be roughly 125,000 meters. So this is in meters. So that's really big. But we need to find a shorter way to write it, because having all these zeros everywhere, it's too much. So what we're gonna do is we're gonna say, okay, so here is where the decimal is. And let's say we don't care too much about the zeros, or powers of 10 are going to cover them. So we're going to move this 0 from here over to here. So we want it to be right there. So we want 1.25. That is much shorter. That is much easier to write. So whenever you move the decimal to the left one place, you multiply by 10. So if we move it once, that's multiplying by 10 once, twice, 3 times, 4 times, 5 times. So we're multiplying by 10 5 times, and that's where the exponent comes in. So, okay, so we can say, 125 kilometers is just 1.25 times 10 to the 5th. So, you start off with the decimal in its normal location. You move it to its new location, which is always, with one number in front of it. And then you just count how many places it's moved over. And as long as you do that, you're all good to go. That's how you do scientific notation. So, but that's when we're moving to the left. Let's look at what happens when we move it to the right, because, always good to have examples going both ways. So, that in mind, let's pick a new number. So let's say we have 3, 4, 5, 0, 0, and put a decimal right there, put a 0. I was like, okay, so now I'm not moving to the left, now I'm moving to the right. So just like before, we are going to multiply by 10. So we have the decimal here, and we want to move it over to here so that we have 3.45. And now we're going to count the number of places we move to the right. So that's 3 places to the right. And since left gave us a positive power, right is going to give us a negative power. So this is a very tiny number. So when the power of 10 is negative, that means you're getting something that's very small, which is okay. That's fine. So if we had this in liters, then this would be a very tiny number of liters. Totally fine. That's exactly what it is supposed to represent. So that's okay. So moving back over here. So scientific notation, power of 10 is negative if the number is very small. Power of 10 is positive if the number is very large. Fair enough. That was exactly what we just described. And then, of course, we got the video here that you can watch. Conversion diversion. So real quick, just want to point out. So this is another one for you guys. The answer you're checking for is in meters. So you got to multiply meters times meters. So the large, long clock, you can get that by just doing, this one times that one because they're both already in meters. But for the big spool of string, you're actually going to need to change these into meters first. So you probably, want to go back to our chart and say, okay, well, we have kilometers. How many do I need to multiply by in order to get meters? And these are the numbers that you multiply by the way. So for the kilo, you multiply by 10 to the third. So you take that number, multiply by 10 to the third, that'll give you meters. Over here we have millimeters. So millimeters, you got to multiply by 10 to the negative third. So you put that up there when you multiply. And then, you'll figure out, do I have how much I need? And if I do have how much I need, how much is it going to cost me? Because you got to kind of check both. So with that in mind. Oh, and also you have to check this guy. Because this guy's already in scientific notation. So we're going to have to come back to that one. And of course, I'll go over this again in the synchronous hours. But that's it for exponents. Next video is going to be over word problems, everyone's favorite. I know everybody loves word problems. So no, I know a lot of people don't like word problems. It's okay, we're going to work on them together. But for now, I'm going to let you go, and I will see you in the next video. Bye-bye.